So one of the things that struck me was just how casual, I mean, that looks like a lot of snow, looks like this, and depending upon how much wind there was and how long it's been, we're talking about a few feet snow in Connecticut. But they just take it all in stride, so no pun intended, but you see that guy with his, just like,
It's just like, oh, this is a normal day.
yeah, it all works, okay? So a lot of times, even though I look at the forecast every morning, like I couldn't remember what it said last night, right? I'm like one of those, because I want to know what to wear, But aside from that, a lot of times forecasters are focused on the severe weather. Remember, don't ever drive your car across something where you cannot see the road, okay, for obvious reasons. So severe weather, we want to know. All sorts of people want to know severe weather. So like, for instance, NASA, and I have a slide here for if you want to go into meteorology, the different sectors, and one of them is NASA really needs to know, Air Force really needs to know what sort of severe weather they might have in times of launching. So the NOAA, in fact, it's taken me a few years to remember what does NOAA mean. Of course, it's NOAA. It stands for National Oceanic and Atmospheric Administration. So I like it. It's new, I think, to this edition where it kind of shows you the flow chart of NOAA. I was like, I never understood how that worked. Now I kind of get it. So on the flow chart here in a minute, you're going to see this, the folks that gather the data, the raw data, are the National Environmental Satellite Data and Information Services. Those are your weather balloon people, for instance, I think. Okay. Then, of course, if you went to spotter training, it was put on by the National Weather Service, and so you're going to see National Weather Service under NOAA, under their offices. And another branch off of NOAA, we have the National Centers. Notice plural. There's multiple National Centers for Environmental Prediction. Under the National Centers for Environmental Prediction, like I said, there's multiple. That there in Miami, the National Hurricane Center, they're part of that branch of NOAA. So the part that we kind of interact with when you're looking on the internet has been more of the local and regional office. Have kind of looked at, again, the data that's been sent them, the models they have available to them, and kind of their firsthand knowledge. So when I took a group of students to Chicago to tour their station there and to meet with the meteorologist, and it struck me that he's kind of like, my model can tell me this, the computer can tell me this, but I've got the final say. I just think that's interesting. So at the top here we have NOAA, National Oceanic and Atmospheric Administration. And then we have the National Weather Service, branches off of that. And kind of a dead end here, we have the folks with their data. Okay. So the National Weather Service actually has 3 branches off of that. The first one are those centers for environmental prediction, the regional offices and others. I'm not quite sure why others are up there, kind of a miscellaneous. So the regional offices would be the National Weather Service. Okay. And then over here, the Centers for Environmental Prediction, the Climate Prediction Center, let's see what else. Storm Prediction Center, do you guys remember where the Storm Prediction Center is? They get hammered. No. And now I'm kind of drawing a blank. Oklahoma. What? Norman, Oklahoma, yeah. Yeah, that's the Storm Prediction Center. That's who gives the outlooks for severe weather in the Midwest, and that's who gives the, not the warnings, but the watches, okay, for severe weather. Yep, Norman. So if you want to go into meteorology, I'm hoping you have a sense for, you need to kind of have the heart of a scientist. That's my plug, okay? So, because it looks like a lot of fun. And actually, probably not today, but Wednesday, we'll look at a few bloopers Meteorology bloopers. Because they use this green screen technology. Yeah, it's kind of bizarre. So if you go into meteorology, you might be the person who presents it. You might be the person who teaches it. You might be in the private sector who needs to know critically what the weather's going to do. Okay, I mentioned NASA, military. I didn't mention NASA yet, but yeah, I did. So if you're into research, there is actually in Boulder, Colorado, there's the place you want to be in atmospheric science, the National Center for Atmospheric Research. And then just to kind of a plug for a meteorologist versus a climatologist. And from what I read from your textbook, it's almost like you become a meteorologist first, and then you decide that your niche really is climatology. So if you watch the movie The Day After Tomorrow, Jack was a climatologist, the father figure. So, yeah. And clear back at the beginning of the course, we talked about the difference between regular day-to-day weather and climatology, or climates. Okay, they're both the condition of the atmosphere, but climates are like a 30-year average. Okay, so we'll be talking more about climates in Unit 5 and climate change. All right. So the thing is we're good with having kind of understanding what the condition of the atmosphere is here. Like, oh, okay, that's us. But in order to understand really kind of what we might be hammered by, okay, we need to think global. So not so surprising then, we have this worldwide effort. It's been going on for a while. But in the area of atmospheric science, it is the World Meteorological Organization, the WMO. Okay. And so these guys are scientists. Like I said, I think scientists play well together, better than politicians. And so members are actually, if you're a member of the UN, then you actually are a member of this atmospheric science organization. So worldwide, we share data. They share data, and it's wonderful, especially with the advent of computers. So then the sites of disseminating that worldwide information, we have one here in the United States. There's one in Moscow, and then there's one in Road Trip, Australia. So I mentioned computers, and not so surprising, computers these days kind of give us our forecasts, and we'll kind of talk about different types of forecasts that computers might give us. But in order for a computer to give you a forecast, it needs to know what the conditions of the atmosphere are. So there are various ways of getting what I call initial conditions. So these are, if you want to put the top, initial conditions, that's what it is. So this actually is one of those getting sea surface temperatures. It's one of those ocean buoys. Okay, sea surface temperatures, but also could get pressure, and I don't know if you can get precipitation, that sort of thing, just to remotely send you the data. There are stations on land, about 11,000 on them, stations on ships, about 4,000 of them, and about 1,200 sea buoys. Bless you. Giving, now this though is the surface, and actually I'm going to switch gears here in a minute and talk about how do we get the condition of the atmosphere at upper elevations. So these are surface. Another thing is folks at these offices, these weather offices, local weather offices, can send information. If you go to spotter training there, and maybe even on if you just watch your local news report at 10 o'clock when the weather guy talks, they actually want people to send them information about precipitation and rainfall and snowfall, because that actually is fed into kind of the central, that's good data. And then down here we have our ASOSs, kind of unique to, I believe, this country. They're a network of automated surface observing systems. Remember, those are the ones usually near airports. But again, this chapter kind of talks about the ASOSs. They're great because they automatically send this data all the time, but there are problems with them. They kind of have little kinks here and there, I guess. So these would be direct data. Okay, So that's direct surface data. What about, and we've kind of got a sense of this already in this class, that what's happening in upper elevations is a player to what's going to happen here at the Earth's surface. So you need to basically have a whole profile of the Earth's atmosphere. Well, one thing we've already talked about are the weather balloons. Okay, so those are sent up twice daily. And the weather balloons can be equipped with either the radio sound or the RON sound. There's kind of a subtle difference. I put it again at the bottom. Radio sound or RON sound. They're little black boxes. The RON sound is great for giving you information about the wind speed and wind direction. But like I said, I just think it's so cool how the little box goes up and it sends information back, probably to the local National Weather Service. And then it basically, the balloon will get too big and the latex breaks and the little box comes back down in a parachute. I just think that's so cute. Anyway, I need to look at some more YouTube videos and find a video of it coming back down. So weather balloons are great, but they are a little bit limiting. Okay, so another way we can get information at upper elevations is by airplanes that are going from point A to B already. So go ahead and slap a measuring device on their belly, make sure it's okay with them. And then as they're flying, you can get information too about wind flow. Then we kind of switch gears to satellites. Now, with hurricanes, we looked just a little bit ago this morning about hurricanes. Satellites actually can get some good information about hurricanes indirectly. I'm going to talk about 3 types of satellites coming up.
Is that a typo? After the word vertical, is that supposed to say profile? Or-
Yeah,
Okay.
yes. Profile sounds French. Yep, it should say profile.
No, it's fine. I didn't even notice. Put an L in there.
Have you ever seen those kind of mind benders where the words are totally misspelled and yet you can read it just because you
Or if you hear it,
If you hear
jumbled
it?
up. No, they had it on brain something. I don't know
Okay,
what it's called,
you
but
can
they
kinda unjumble.
jumbled up, and they heard it like 4 times, and then by the 3rd or 4th time, they're like, I know what it's saying. I just thought that was crazy.
our minds just kind of do interesting things. We can also use this type of radar called a wind profiler. Regular radar, actually Doppler radar. Okay, so those are all different ways of getting a sense for what is the condition of the atmosphere at upper elevations. All right. So, we're going to talk about weather forecasting, and if you're like me, we're used to looking at kind of a forecast map of like what tomorrow's going to be. But a synoptic map is what is it now. A synoptic map is a snapshot of the conditions right now. Now, it could be conditions at the surface or it could be conditions aloft, synoptic maps. But if you look at the conditions, what they are now, you're getting a sense for maybe coming up with a forecast from what they are now. So synoptic map. So we looked at this cute little icon called a station model before that kind of gives you a lot of information about a location in one little icon. And so you're going to see station models coming up on these synoptic maps here in a minute. Synoptic maps, getting a snapshot of the atmosphere. It's not just the Earth's surface, but you're going to see synoptic maps at different elevations, and I'll kind of talk you through that. And as you look at these synoptic maps, keep in mind that nowadays the computer, assisted by humans, kind of print these out, but they used to be done like by hand. And there are some like kind of some cool historic weather maps out there. You're like, oh my gosh. Okay, so I know it's hard to see, but that's a synoptic map. It's a surface map, which you wouldn't necessarily know. And you might recognize Let's see, let's pick this one in Missouri, Illinois. Okay. Let's pick on that one, and we see two temperatures. Do you guys remember? I see 42 and 31. What's 42?
Actual temperature.
It is the actual temperature, exactly. So that's the actual or current. And what is 31?
Dew point.
Dew point temperature. Very good. Dew point temperature. Perfect. So that's the station model. And so the title says, where would you draw the fronts? Now, I think we had kind of a little bit of exercise doing that, trying to find what was cold and warm. And I'll just tell you that this is what you end up doing. I'm drawing a front between these air masses. Okay? So let's see if we can find an air mass that would be cold versus moving in on warm air. So, for instance, on either side of that blue line, I'm not saying I could necessarily find it through the trees. Weeds, okay. We got a current temperature of 47, dew point temperature 35. I buy that, and kind of staying at the same latitude, it's like a 20-degree difference. Okay, so definitely we have some sort of cold air mass here and a warm air mass here. So, synoptic map. So this is another synoptic map. It's like a mixed map, though, because I can tell that because it's kind of showing radar information. The green, which of course is precipitation, the green, the yellow, the orange, and the red, that's precipitation. And you get that from ground radar. So that is actually surface map. Now this is our first upper elevation map. Okay. Now we talked about isobaric maps. Let me kind of remind you how that works. I didn't talk a lot. But this one is a 500 MB, 500 millibar isobaric map. So you're like, what the heck does that mean? And it almost looks like we have isobars there, because you can kind of see the patterns. So a 500 millibar isobaric map. Do you guys remember at the Earth's surface how many millibars that is about? How many millibars sea level pressure?
16.
Nope. Have a nice rounder number. Just on the other side of 1,000, so about 1,013. Thank you, though. About 1,013 millibars. Okay? So that is actually the weight of the air here. So to get 500 millibars, do you think, do you buy this, you have to go up in elevation? 500 millibars. It seems like about halfway up, but remember, it's a lot squished, it's a lot denser here. So you go about this high up and you get about 500 millibars. So what these are ISO heights. I don't know if you remember that. I talked about that before. These are ISO heights. These contour lines say how far do you need to go up in order to reach 500 millibars. So that is your 500 millibar isobaric map. Again, it's a synoptic map. But you can already see some kind of, you see some numbers on those contour lines. Those are ISO heights. And you can kind of use ISO heights with isobars a little bit interchangeably. So,
It's kind of confusing. What do you mean, like, the amount that you have to go up?
their elevation, I think they're meters above sea level in order to get a pressure of 500 millibars. They're ISO heights.
So that's what those numbers, like 18, 24, like all those.
These over here, that's what these are. The 588, the 582, the 576. That's what those are. So if you kind of remember that, that's 500 millibar isobaric map. And actually, I've got a few more to show you. I've got an 850 and a 300 and a 200 to show you. So for instance, with the 200, does this make sense? It's going to be way up here, the 200 millibar isobaric map. The 850 millibar isobaric map is going to be right here. So it's interesting.
So from 850 to 500, how many feet? How do you know how many feet is a millibar?
That's where the actual conditions come in. That's where it's been measured to see where your pressure differences lie. It's like fine-tuning the differences in pressures by going with this ISO height instead of, and it's looking at layer of the atmosphere. So
Kind of varies.
it would vary. Yes, definitely. So there's an 850 millibar isobaric map. Okay. Oh, that's why it threw. Now these contour lines are, not to totally confuse us, because these contour lines actually are isotherms, or the red ones are isotherms. Let's see. So again, these are synoptic maps, a snapshot of what the conditions are. And the other thing I wanted to note is we kind of talked about cold air pushing down, warm air pushing up. We talked about troughs and ridges. Can you kind of see this is maybe kind of working for you? What's this one down here, what we call this, a trough or a ridge? It is a trough, very good. And then what is this? It is a ridge, yes. So we would think of low pressure here, high pressure there. So low pressure here, okay? It's all kind of... so taking it up a notch, so that was 850, this is 500. And so I'm not sure why the other 500 was so low. But this makes more sense. These numbers in, again, I think they're meters that you need to go in order to get, in this case, 500 millibar of pressure. So the different layers would give atmospheric scientists, the different layers would give them different information. So at this elevation, it's going to be good for understanding movement of your large weather systems like your mid-latitude cyclones. So, and this is all the same day, I think. So that's going up from the 850, and this is going up from the 200. So 200 millibar isobaric map. And I think, Joshua, you were asking, like, how far up do you need to get to this? This is about 6 miles. I think the other one was, did it say 2? This is about 6 miles up, pushing the edge of the troposphere. So here, finally, we get a look at the jet stream. That pink over there, that's your jet stream. The jet stream is just a fast-moving ribbon of air that's between what your feral and your polar cells. So it's a chilly negative 75 degrees Fahrenheit, approximately. So by the time you look at those 3 or 4 synoptic maps, you definitely kind of get a sense for what the atmosphere is doing. Okay, so as far as forecasting, because just kind of in general, kind of keep, this is a recall slide. If your jet stream is relatively strong, actually it can screw up your hurricanes that are trying to strengthen. It kind of messes up their development. But if your jet stream is strong, actually that can strengthen your thunderstorms. Because we talked about wind shear. If your jet stream is strong, that can impart wind shear that actually thunderstorms thrive on. So the weak jet stream is the opposite. So if your jet stream is kind of on the weedy side, then actually that is going to enhance your hurricane activity and diminish your thunderstorms. All right, so that blank slide is to remind me that that's a good place to stop. Okay, so I don't know, I think it might take us the whole time to get through forecasting Wednesday. We'll just see. Okay. So chapter 12 assignment is due.
11.
Thank you, 11 is due Wednesday.
But on Facebook thing,